Okay, all right. If you could please keep quiet. Sorry, the situation here is not ideal. The table's very low, so it's not great for my back, but also it's not great for the audio pickup, for which I need to be quite close to the machine. So I'm going to be a bit hunchback today. All right, so level curves. This is another name for contours. Okay, so level curves. Okay, so let me actually back up a bit to trace, which is an abbreviation of my name, but it is also the curve you get. The curve you have when one of the three variables in a surface equation is held constant. One of the three variables in a surface equation is held constant. Oh, sorry, the stylus isn't keeping up with me. Oh, man. Come on, I want rubber. That must go away. Whew. Hello. Wake up. Held constant. Okay, the curve you have in one of the three variables in a surface equation is held constant. So for instance, here's an example. Well, let's have a look. What's the simplest possible example? Probably a sphere. So x squared plus y squared plus z squared equals 4. Come on, stylus. Equals 4. There we go. That's a sphere. Oops, z squared. That is a sphere of radius 2. Okay, so now you can hold a particular variable constant. When we hold it constant, we don't actually give it a number. We give it a sort of a mystery constant, generally k. So x constant, and it'll be k squared plus y squared plus z squared equals 4. Or what we would normally write is y squared plus z squared. Golly. 4 minus k squared. All right, and that, of course, is a circle. It's a circle of radius square root of 4 minus k squared. So that is a circle, or more precisely, it is a family of circles. Of radius square root of 4 minus k squared. Okay, now because we can only square root positive numbers unless we're working in the complex arena, which we are not in this course, which is a real shame. It's the one thing I miss from teaching first year maths is no complex numbers. Sorry, you're going to miss complex numbers this semester, but I'm sure you'll see them again in 2084 if you haven't done 84 yet. Okay, so because we can only square root positive things, that does kind of place some restrictions on what k can be. But that makes sense, because if you think of a sphere of radius 2, it only goes out as much as 2 units from the origin. Okay, it doesn't get further than 2 units from the origin. So it doesn't make sense to set x to anything beyond 2 or smaller than minus 2, because there is no surface there. So in a sense, what we're doing is we're taking a sphere and we're slicing it with a plane x equals k. And then we're looking at the curve that we get at that intersection of where we're slicing the sphere. Okay? And so the values of k can take on, let's have a look, k can lie between minus 2 and 2. And because this is such a symmetric formula, we're going to have something very, very similar for all of the other traces. Okay, so hold y constant, and we're going to end up with x squared plus z squared. Once again, we're going to have a family of circles. and hold Z constant, and we'll have x squared plus y squared equals 4 minus k squared. And once again, it'll be that same family of circles. If we were going to draw those circles on a two-dimensional drawing, then of course in the first case we'd label our axes y and z, in the second case we'd label our axes x and z, and in the third case we would label our axes x and y, but other than that the pictures would look the same. Okay, so those are called traces. Now, sometimes if you look back and past, I know that when Yuri Conradi convened this course, when he convened 2083, he was very fond in exam papers of asking for traces in a plane. So he would ask for the trace of the sphere in the YZ plane. Now you know that in the YZ plane, x is 0. So basically, he would be asking for holding x constant at 0, and then you wouldn't have to put a k in, you would actually put in a 0. So sometimes you're asked for a specific trace. More generally, you're asked for a general trace, in which case it's a family of curves. Okay, now, usually in tests and exams, we don't ask you for any old trace. We usually ask you for that last one, holding z constant. And in this case, it has a special name, okay? This one is called the level curve, or the level curves. And the most common place that you are likely to have run into level curves in just everyday life is on a map that has contours on it. If you've ever looked at a geographical map that has contours drawn on it, heights above sea level, so you have lots of little squiggly curves showing where the mountains and things are, then what you're looking at there are level curves. You're looking at the curves that you would get if you sliced horizontally, if you sliced through the landscape at z equals 100 meters, at z equals 200 meters, at z equals 300 meters, and what is being drawn there on those contours are those curves of intersection between horizontal planes and your landscape or your surface. Okay, so level curves are traces. They're the trace where z is held constant. Okay, so if you look in past tests and exams, you'll find lots of questions like this, asking for level curves. Now, if you look at a geographical map, you can tell roughly what the landscape looks like by looking at those contours. You can tell there's a mountain over here and there's a valley over there, and you can tell that the mountain is quite steep because the contours are quite close together, so you're going from 100 meters to 200 meters to 300 meters really fast. Or you can tell where the highest point on the mountain is going to be, and things like that. So you can tell what the landscape's going to look like. So just like on a geographical map, you can tell what a surface is going to look like by looking at its family of level curves. Now, unless your surface is a really obscure surface, after a couple of weeks, or maybe after 1 week in this course, I'm going to expect you to recognize what your surface looks like simply by looking at its equation. When you look at a sphere equation, I don't want you thinking, gosh, what is this? Let me draw the level curves and figure it out. I want you looking at a sphere equation and going, oh, that's totally a sphere. And that goes for all of the common surfaces that we're going to be using in this course, which you will find on pages 17 and 18. So if you look in your handbook on pages 17 and 18, those are called quadric surfaces because their formulas all involve sort of a quadratic in some way, x squared or y squared or z squared. Okay, so page 17, 18, quadric surfaces. Okay, more people are coming in. I'm just looking at seats. As far as chairs go, we have quite a few chairs because there's some there. It's just there's not a lot of table to go with the chairs, but there's some. Okay. Oh, and there's some at the back there, right? Yeah. Okay. So there is still some space, but not a lot. Which is, I have asked for a bigger venue, so this is why 2083s I'm delaying signing you over into 85. Because if we can't get a bigger venue, then we're going to have to make some harsh decisions and say goodbye to our 2083 friends. And I'd rather not do that. Okay. Lecturers who have some control over when their lecture can be never choose first period. Okay, because, what sane person wants to get up for first period? So I'm hoping that there are some venues available in first period. Because of that, it's an unpopular time slot. I do not have any control over when my lecture is, and I've been teaching in first period. I can't remember not teaching in first period. A friend of mine in the law faculty the other day who I think she teaches postgrads, and she's got a lot of control over her time, and it's all in the afternoons, and it's kind of block teaching, and she discovered that I teach in first period every day, all year, and she said I should just get promoted to professor just summer because of this huge sacrifice. So I'm hoping that we will get a venue, but I asked yesterday, shortly after the lecture, and certainly nothing has happened yet, so we'll see. But the secretaries who do that sort of thing are very busy at this time of year, so we'll have a look. Okay, all right, so level curves. All right, so let's do an example. So a typical example would be number 3. Okay, number 3, so could you please keep quiet? When you're quite ready. Number 3, it's page 16. Okay, so I'm going to do number 3. And it says, plot the level curves of the following functions. For each of them, plot several curves and label them sensibly. What does the surface look like? Now, in a test or an exam, it would probably not have that middle sentence. It would probably just have plot the level curves of the following functions. But the level curves are always a family of curves, so you have to draw several. I'd suggest 3. 3 is a good number. You should always label them. So you should say, this is the one where k equals 0, and this is the one where k equals 1. And the reason for labeling them is not so much so that you can see which curve belongs to which k, but so that you can see what's happening to the curves as k gets bigger. Are the curves moving away from the origin or closer to the origin, bigger, smaller? What is happening to the gaps between them? So you want to see how, just like with a geographical map, you can see how steep the mountain is by looking at how close the contours are. There's information to be held in not just what the curves look like, but how close they are together, and whether your surface, in a sense, is going up or going down. Okay, is it like a bowl that's been turned upside down, or is it like a bowl that's the right way up? And you can tell that from what's happening to the curves as k changes. Okay, so let's do number 8. This one is f of xy, and you could write z there for that f of xy, equals x squared minus y squared. Okay, so what you would do, the very first thing you do is you replace the z with a k. Do that straight away, okay? Let's say there was a square root on... Let's say that x squared minus y squared, I'll get to that then. But basically what I'm saying here is replace the z with k straight away before you do any sort of fiddling with the formula. Okay, and then you've got to know what kind of curve that is. So what kind of curve is that? You tell me. What's a family of curves, to be precise? Did you do conic sections in first year? Yes, of course you did. May not have called it conic sections, but you'll have done it. I'm sure some of you have already done 2084, in which case also conic section should be familiar. Go on. Does nobody know what that is?
It's the hyperbolic paraboloid.
Okay, well, the surface is a hyperbolic paraboloid, yeah. This is a hyperbolic paraboloid, quite right. Nicely looked up on the table. Okay, I can see. Okay, some people are being brave and are putting their ideas out there. That is a family of hyperbolas. Okay, not the good old-fashioned hyperbolas that you did at school, which looked like x times y equals k, which are also hyperbolas. Those are hyperbolas that have the x and y axes as their asymptotes, okay, x, y equals k. Those hyperbolas sit very neatly inside the quadrants. These hyperbolas have their asymptotes like an x, okay, and so they kind of turn 90 degrees from those x, y equals k hyperbolas. You honestly never seen these? Surely you did conic sections in first. What are they teaching? I'm getting old. What are they teaching the youth nowadays? Here we go. So, who of you familiar with the Narnia books? The Professor and the Magicians and the Magician. Well, yeah. And he becomes a professor in The Lion, the Witch, and the Wardrobe. And he's like, what do they teach in the schools nowadays? Here we go. Okay, so here we go. So such a nice simple thing where the x squared and the y squared their coefficients are 1. These will be nice simple asymptotes. There's ways of working out the formulas of the asymptotes. I'm not going to do that. Okay, so hyperbolas that look like this, just like in the x, y equals k hyperbolas, they're either sitting in the first and third quadrants or they're sitting in the second and fourth quadrants, depending on whether k is positive or negative. Remember that from school? Are you even listening? Right, hyperbolas, they always come in pairs, right? The school ones were either first, third, or second, fourth. These ones are either top, bottom, or left, right. So how do you know which ones they're going to be? Now, I can remember in last semester's class, so some of the students had these funny, weird ways of remembering. I just look at that formula and go, well, let's say that k, what I'm going to write here now, I'm going to rub out in a moment. But let's just look at that. Let's look at the simple case for k equals 1. If I want to solve for my axis intercepts, like where this curve cuts the x-axis, where this curve cuts the y-axis, I will be able to solve for such information if I'm looking for x. But I will not be able to solve for that information if I'm looking for y. Because if I'm looking for x, I'll set y equals 0, x squared equals 1, not a problem. If I'm looking for my y-intercept, I'll set x equal to 0 minus y squared equals 1, problem. So that 1 equals x squared minus y squared is going to give me left-right hyperbolas, ones that cut the x-axis but don't cut the y-axis. So they'll look like that. But you can see that the opposite is going to happen if k is negative. Sorry, it's a little bit wobbly. Okay, actually, I'll leave this here. This will be a left-right hyperbola. But what if it's minus 1 equals x squared minus y squared? Now it's possible to solve for y, but not possible to solve for x. So these are top-bottom. And if you don't think later on in several months' time when you're rereading your notes, if you think that LRTB is not going to make any sense, then write out left, right, top, bottom, yes. We don't. K could be anything. Good question. K is a constant that could be anything, unless there's some constraints like the thing I did just above that I've scrolled past. K did have some constraints because there was a square root involved and we couldn't square it to negative. But here, there's no constraint. K can be anything, which means... Oh, golly, I'm drawing terrible hyperbolas here. Please draw meter drawings for man in your notebook. When I put the solutions up on Vula, I cleverly drew them on a graphics program, and so the one that'll go up in the solutions on Vula is much prettier than this. Okay, so these ones over here go with k greater than 0, and these ones over here go with k less than 0. And what if k actually equals 0? Is that possible? It is possible, yeah. There's no reason why k shouldn't be 0. There's no log of k or anything in there, or 1 over k. So if k equals 0, I'll have x squared minus y squared equals 0. And what kind of curve is that? I heard a voice, but I didn't. It would be x equals y or x equals minus y. So in fact, those asymptotes that I've drawn dotted, they will actually be the curves in the special case for k equals 0. So this is a very busy drawing. Okay. Let's have a look. I'm going to... You should try in a picture of level curves to draw important points like intercepts, or if it's a circle, maybe the center. You should try and draw some important points for at least one of the curves. So let me make this first curve here, k equals to 1. And it'll cut over here at 1, and it'll cut over here at -1, and I'm going to leave it at that, because you can see that if you put too much detail into a level curves picture, it can quickly get overwhelmed. Okay, I don't really like level curve questions. I find that they take, if you want to draw a really good drawing, it can take you ages. And in a test or an exam, no, you've got better things to do with your time. If I set a test or an exam question that asks for level curves, I'll make them pretty simple level curves. Just so that you can draw them nice and fast, and they're not something you need to stop and really think about. Yeah, what else is there to say about level curves? Okay, if all of that just completely disappeared and I said, okay, you do that, would you have been able to do it? Of course you could. Oh my goodness, it's a very quiet class. No, you got to develop some energy. Come. We're going to have maths energy. Yes, engineers all love maths. The next one. Engineering, frankly, is applied maths, as far as I'm concerned. So you are, in fact, doing a degree in mathematics. Face it. Go home and look in the mirror and go, I, so-and-so, am doing a degree in mathematics. I need to accept the truth in this. It's just, maths wearing engineering clothes. Maths used for application to the world and society. Okay, all right, so this one, very similar. Only this time slightly more recognizable family of curves there. Those are circles of radius k, okay? Not circles of radius k, circles of radius root k. Circles of radius root k. Oh, there was something I left out above here, although I suppose it's implicit in the picture. But I never said what the constraints on k could be, but in fact k can be an element of R. There are no constraints. Frequently there are constraints on k. For instance, let's have a look here. K cannot be negative. X squared minus y squared equaling a negative, not a problem. X squared plus y squared equaling a negative, not possible. Okay, so here we have k has to be greater than or equal to 0. Okay, so negative k's need not apply. What do we have? We have circles. We have a family of circles. Okay, so let's just think about this now. If I let k equal to 1, I'll have a radius of 1. If I let k equal 2, I'll have a radius of root 2. If I let k equals 3, I'll have a radius of root 3. If I let k equals 4, I'll have a radius of 2. So as k increases in equal increments, are the radii increasing in equal increments? No, they're not. So when I draw those circles, they're not going to have equally spaced gaps. Are the gaps going to get smaller as I go out, or are they going to get bigger? So the first radius is 1, the next is square root of 2, which is what, 1.4 something? The next one is square root of 3, which is what, 1.7 something? And the next is 2. I think the gaps are getting smaller. Once again, this is obviously something that's much easier to see if you draw it on a computer where it will be drawn accurately. Oh, Tracy, come on, come on. Okay, now let me try and draw this one closer. Closer, come on. It's particularly tricky when the stylus doesn't quite do what I want it to do. There you go, blaming my tools. Bad workman blames her tools. Here we go. All right, so this is k equals 1, k equals 2, k equals 3, k equals 4. So that'll be a 1 over there, and that'll be a 2 over there. There's my x, there's my y. And that's probably good enough, actually. Is there anything else that needs to be done? I've labeled some Ks. I've tried to show what's happening with the gaps. I've put in some intersections. X, Y. Ooh, back in my previous picture, I don't think I put in X, Y. That was naughty. Oh, my high school teacher would be cross with me, girl. She taught me good habits. Okay. So level curves they're not really hard, but they're a little bit tedious. Okay, and now from those level curves, you can figure out what your surface is going to look like, although, as I said, I would prefer that you just looked at the formula of the surface and knew what it looked like. But we can tell that if we slice it horizontally, we're getting circles, okay? That's nice. And what happens is that as we go further out, even the circles are getting bigger, but they're getting bigger slowly. So what's happening is we have a paraboloid, which goes outward, but as you go outward, it kind of steepens up. Okay. Z equals x squared plus y squared, paraboloid. You can also tell it's a paraboloid by looking at the vertical traces, the ones if you set x or y constant. Because just put your thumb over the y, you'll have z equals x squared, parabola. Put your thumb over the x squared, you'll have z equals y squared. These are parabolas. So if you look at it from the side, you're seeing parabolas. Look at it from the top, you're seeing circles. Paraboloid. Okay, all right. And so surface up here is hyperbolic paraboloid. Hyperbolic paraboloid. Well, first thing is try and use that before nightfall in casual conversation and impress your friends. Secondly, it's a saddle. Okay, it's a saddle just like a horse's saddle. Okay, it's a saddle. It's if you look at a saddle, parallel to the horse's spine, it looks like a happy parabola. Okay, where you put your bottom. Okay, but if you look perpendicular to the horse's spine, it's a sad parabola where your legs go. Okay. Also, I don't know a lot about geography, but I think saddle, in fact, is a term used in geography as well, where if you've got two hills in front of you or two mountains in front of you, then the lowest point between those two mountains is often kind of higher than where you are. So to get there, you have to go up and then down to get through the mountain pass. So you're going up and then down. But if you were going from the one mountain peak to the other mountain peak, you'd be going down and then up. So hyperbolic paraboloid. It's a pretty cool surface. So that's what's going on in part A. This one here is a paraboloid. The surface. Paraboloid. We're going to deal with paraboloids a lot. You're going to know everything there is to know about paraboloids. So have a look at part C. Part C, x equals square root of x squared plus y squared. So now let me demonstrate what I meant by replace your z straight away. Okay, yeah?
And was the surface from A the hyperbolic
Paraboloid, that's right. Okay, so this, of course, this f of x, y, of course, is z. So now here is a common mistake. The common mistake is to first square out, because you don't like the square root, and then replace the z squared with k. No, you're replacing z with k, not z squared with k. Okay, so this is a common mistake, to go from the z squared to the k, because you first fiddle with your equation, and then the thing you end up replacing is not actually the z. Because then the curves that you're going to get are not actually going to do what they're supposed to be doing. Because that's going to look like a paraboloid again. The circles that you're going to get are going to look just like the picture above. However, the picture you're supposed to be getting is a family of circles, but it's a family of circles with radius k, not radius square root k. Because your r squared is k squared, so your r is k. So as k increases in equal increments, your radius also increases in equal increments. So once again, you get a family of circles, but this time evenly spaced. I'm running out of space on the page. I'll do it over here. So let me try and draw some circles evenly spaced. Okay, so if they're circles evenly spaced, what sort of surface do you think it is? Oh, golly. Okay, I'm trying to draw them evenly spaced, not with a great deal of success. There we go. There's my x, there's my y, there's k equals 1, k equals 2, k equals 3, k equals 4. Okay, so before with the paraboloid, we had a circle, then we had a bigger one, and then we had bigger but only a bit bigger, and then we had bigger but only a bit bigger, and so we had this steepening of the sides. Now we don't have a steepening of the sides. We have circle, and then circle, and then circle, every time the same increment bigger than the previous one. So what kind of surface will that be? You can, cone. Yes, I'm hearing some people say cone. That's a cone. Okay, so here, there's a little bit of an ambiguity in wording. Did I write it in here? Yeah, I kind of did. So if you look at that box on page 17, the second one from the bottom is the cone. Now, if your formula looks like z squared equals x squared plus y squared, then of course z could be positive or negative, in which case you have a cone that, okay, I'm just going to do a little scribbly drawing here, which I'll rub out in a second, in which case it'll look like that. Now, to some mathematicians, that is a cone. And if you're actually only taking the ice cream cone part of it, or the road cone part of it, it's a half cone. Okay, so what we would have in this particular one here, 3c, would be a half cone because it's only the top half. However, there are other mathematicians who say, no, that's silly. Even if it's only an ice cream cone, it's still a cone, or a road cone. It's still, so there's a little bit of a disagreement amongst mathematicians of the correct term to use. And if you look back through old resources for this course, you'll sometimes see the word cone applied to this square root formula, and you'll sometimes see the word half cone applied, and it depends entirely who was the mathematician who was typing up that particular tat on that day. So it's just not something for you to worry about, but you might run across that term half cone. And a half cone just basically means what we think of as a cone. It's just half of that picture on page 17. Okay, so cone. Let's have a look. K has to be positive, but can K, oh, so here we go. K has to be positive. Can it go on forever? Or is there some sort of upper limit to K? And can it be 0? Well, let's address those one at a time. Is there an upper limit to K, or can K be anything? It can be anything. There's no reason to restrict K. K can be anything. X squared, if we just make X and Y sufficiently large, the square root of X squared plus Y squared also be very large. So so K can go up to infinity. Okay, and I've already put an equals in there, but is it true? Can K be 0? It can be. If X and Y are both 0, then K would also be 0. So you have to kind of think of the range of K, the interval that K can fit into. Anything else? Anything else? I haven't put in any intercept, so let's put in a 1 over there, and let's put in a 4 over there. There we go. I've already said what the surface is. Try number 4. Question.
The thing that those are on the XY, I think you have 1 and 2.
Yeah, so in part B, those two intercepts are 1 and 2, but in part C, they're 1 and 4, because in part B, I'm square rooting the K to get the radius, and in part C, the radius is K. Is that addressing your question? Did I understand your question? Maybe? Okay, cool. All right, so you try number 4.